pictures. So let's see. A monomial. What does the word, the stem mono mean? One. So monomial, and that was beautiful, is a one-term expression. So for example, a one-term expression could be a number. So for example, the number 8. It could be a variable. So give me a variable. X, okay, it could be an 8. It could be an X, or it could be a combination of the two, such as 8X, or 8B, or 12X, or 12Y, whatever. You know, I was trying to do a different letter, it didn't work so well. So those are all monomials. Now, a polynomial is either a monomial, right? So a one-term expression is a polynomial technically, or it's the sum of many monomials. Now, what does the word, the stem poly mean? Many. And do you know what nomial would be? Nom actually means term. So nomial means term. So this translates to many terms based on its stem. So you've seen monomials or polynomials, I'm sorry, I got my words all mixed up, many, many times. So it could be something like 17x to the 5th plus 3x to the 3rd minus x plus 1. That's a polynomial. There are many terms being added or subtracted together there. All right, now the next one is a word you've known. We did this with quadratics, and it's called the standard form of a polynomial. Arranges the terms based on their exponents in descending order. All right, so that means the exponents go from highest exponent to lowest exponent. And then we learned this on Friday that the degree of a polynomial is the highest exponent that it has. So when you're writing the polynomial in standard form, it's the exponent on the first term. Okay? So we have all kinds of names because it just wouldn't be English or math without a lot of different names for similar things. So we're going to name our polynomials based on their degree, what the highest exponent is, and then based on how many terms it has. So let's start. Let me kind of walk this off here. Let's just look at the left half to start. So if I have a polynomial that has degree of 0, that would be something like 5, right? The number 5. That is actually called a constant. So anything with degree 0 is called a constant. All right, now degree 1. Remember, degree is the highest exponent, so if I have x to the first, that'd be degree 1. And what do you know what we call degree 1 polynomials? If you graphed this, what would it make? So what's x equals 4? A line, so it'd be a linear function. So degree 1 polynomials are called linear. All right, the second one is 4x squared. What's the degree of this polynomial? 2. And what do we call degree 2? Quadratics. So it's not a parabola, that's the graph it makes, but the name is called a quadratic polynomial. All right, the next one is called degree 3. Highest exponent is 3 right here. Anyone know the name for that? It starts with the letter C. No? I was giving you, it's called wait time in education. If you ask a question, you have to wait for a second. 10 minutes. Oh, wait that long. It's called a cubic polynomial. Cubic. So you're actually going to use those more. We'll do them in this unit, but you'll use those more when you get to pre-calculus. Degree 4. Right here. That's called a quartic. Q-U-A-R-T, like a quart of milk, or a quart of something. A quartic polynomial, the stem quart means 4. And based off of those kind of examples right here, what do we think we call a degree 5 polynomial? Not quintic. That's another, what's another stem for 5 though? Quintic. See, this is why the English language is so horrible to other people. Because we have cubic here, but we know the stem for 3 is tri. For 4, we have quad or quart. 5, we have penta and quint. Like, it just, you know.
Is that why the
Quintuplets, yeah. Quadruplets is 4. Let's see, the other, for 2, we have quadratics, but we also have the word bi or do, also all mean 2. Like, why do we have so many stems? Why do we make it confusing? But those are the names based on degree. Now, we're going to focus mostly on that column, right? So these are the ones that are important to us, the left hand side. The right-hand side, we kind of already know these, but these are names based on how many terms you have. So, for example, if you have 5 as a constant, there's only one term here, and we learned up above a one-term expression is called a monomial. Okay? That one-term expression is called a monomial. Now, in this expression right here, how many terms are there? 2. And we call that a binomial. Think about like factoring. We factored binomials. So if you have, so that is actually a linear binomial, if you wanted to be super formal about it. How many terms does this quadratic have? How many terms does it have? Just, is there any plus or minus signs? No, there's no plus or minus, so that just has one term. So this is also a monomial. How many terms? This one does have 3, and it's called a trinomial. There we go. We just got excited before. Quartic. How many terms are in this quartic? That one has 2, so that's a binomial as well. And finally, how many terms are in the quintic here? 4. Now, unfortunately, there's not a cool name for this. It's just called a polynomial of 4 terms. So that one, for whatever reason, I guess whoever created these got really bored or tired after 3 and decided they were just polynomial of 4 terms, of 5 terms, of 6 terms. From here on. Yeah, like we're done. So here's what we're going to do. We're going to practice this thought. Now, I'm going to make this kind of a shortcut for some of us. We're going to focus only on this left hand with the names from this left hand of the chart. And I'm going to assign each row a problem down here. You're going to put your problem in standard form. Tell me the degree. Tell me the classification based on its degree. All right, so as we go through this, again, classified by the degree is using these words on your left. So row 1, we had 2 rows that did this. So someone from there, can you tell me what you wrote as the standard form? Bobby, go ahead. Standard form is? Okay, someone else. Yeah, okay, that's standard form. What's the degree of that polynomial? 2. And what do we call degree 2 polynomials? Quadratic. It says write each polynomial in standard form. Why? Because that's how we write things in math. Always highest lowest exponent. It's the convention. It's how things are done. All right, group 2. Nate's row here. What's the standard form? X to the 4. Now what happens with these x squared ones? They combine to be plus 4x squared plus 4x minus 12. Great job, Lisa. What's the degree there? 4. And what do I call polynomial degree 4? Quartic. Alright, next row here. What is the standard form for number 3? I'll start you off. 3x cubed minus x plus 5. What's the degree there? 3. And you call that a cubic polynomial. Alright, last one. What's the standard form for number 4? And minus 4x squared. The degree is 5, and you call that a quintic. Alright. right, so those names, especially linear, quadratic, cubic, quartic, quintic, those are names that you need to remember. So we're going to pop over here to the next page. We're going to talk specifically about what the degree now tells us. The degree tells us a lot. So it tells us the name of the polynomial. It also tells us three other things that we're going to look at the rest of the time. It talks about the end behavior of the graph. Now on Friday, we said that had to deal with where the arrows were going, what the ends of the graph look like. So we're going to formalize that today. The second thing that degree tells me is the maximum number of turning points. So we'll look at that again. And then finally, the total number of roots that a graph has. Now roots here do not just mean X-intercepts. It does mean real X-intercepts, so that's what a real root is. How many times you cross the axis. But the imaginary roots also are counted in that total. And imaginary would mean that the root has an I in it, which we will explore later on this week. But so the roots are real, X-intercepts, and imaginary. Let's start with end behavior. We have some graphs here. So we're going to look at the arrows or the ends of the graphs. So first thing I have, I'll start here on the left graph. Y equals x squared. What is the degree of that polynomial? 2. So what do I call it if it's degree 2? It's quadratic. Now, it says here A is what we call the leading coefficient. So it's the number that's in front of that polynomial. What would the leading coefficient be? It's positive 1. So we're going to write the word positive in here. So in this case, the leading coefficient of this graph is positive. That's important for later. Now here's how we formalize end behavior. We have these infinities and arrows. And what this says is that as x approaches negative infinity, so as x approaches negative infinity, would you think that that means it's going to the left or going to the right? The left. So as x goes to the left over here, where's the arrow going? Up towards infinity. So as x goes to the left to negative infinity, the y is going up to infinity. Okay, so then as x goes to positive infinity, or the right, my arrow is going up to infinity. That's how you write end behavior formally. All right, let's look at the next one. What's the degree of this second polynomial? 4. So we call it a quartic polynomial. Now the leading coefficient here is negative 1. So that means I have a negative leading coefficient. So here, as x goes towards negative infinity out to the left, where's the arrow going? Going down towards negative infinity. And as my arrow goes to the right this time, where's the arrow on the right going? Negative infinity. Now, before we get to the next two graphs, let's pop down to the words underneath. It looks like if my degree is even, so 2 and 4 are even numbers, right? So my degree is even. It means that both arrows go towards positive infinity, or they both go towards negative infinity, right? We saw that on Friday in our activity. We said both arrows went up or both arrows went down. So what do you think the relationship is between the leading coefficient and where the arrows go? If the leading coefficient is positive, where do the arrows go? Up, towards infinity. So that's your first point. So our degree tells me that both arrows go in the same direction. The leading coefficient tells me which way the arrows point. So if I have a negative leading coefficient, I go towards negative infinity. Okay. Now this is probably the hardest part to get, because when we do our quiz on Wednesday, we'll do a practice problem later, but there'll be no calculator, and you have to be able to tell me where the arrows are going without a picture. Okay. Now the last two. What's the degree of the third graph? 3. So what is the leading coefficient here? Positive 1. So it's positive leading coefficient. Alright? So as I go to the left, as x goes to negative infinity, the y values go towards negative infinity. And as I go to the right, where are the y values going? Positive infinity. Okay. Last one, the degree is 3, and I forgot to ask you the last time, what do I call degree 3? Cubic. The leading coefficient is negative. And this time, as x goes to negative infinity, where's my arrow headed? Positive infinity. And then on the right, I'm heading to negative. So let's talk about what this does for our graph. It looks like that if my degree is odd, so here we have 3, 3 is an odd number, one arrow is going to go up towards infinity, one arrow is going to go down towards negative infinity. Now, if my graph has a positive leading coefficient, so we know if it's odd, the arrows go in opposite directions. If I have a positive leading coefficient, I say if I were to draw a line between those two arrows, my graph has a positive trend. All right, so that means it starts low and high. That's a positive trend. If I have a negative leading coefficient, I can say I start high and end low with a negative trend. Does that make sense? All right, so my degree tells me the name of my polynomial, and it helps me to know where the arrows are going. The next thing my degree does is it tells me how many times my graph changes direction. So we will start with degree 1, which is called a linear function. How many times do you think a line can change direction? None, right? Have you ever seen a line that turns in the middle? So we can draw any line you want. I'll just draw one that looks like this. But no line can ever change direction. And when you think about the arrows now that we know a little bit about end behavior, is 1 even or odd? Odd. So that means since it's odd degree, the arrows have to go in opposite directions. So I can't go in opposite directions and ever turn. All right, degree 2, quadratic. It has to turn how many times? Think about parabolas, just once. There's no parabola that can turn 0 times or 2 times. So draw any parabola you want there. I'll just draw this one. But again, think about the degree. Degree 2 means the arrows go in opposite or the same direction? The same. So if these have to go in the same direction, they both have to be pointing down or up. So I can only get that with one turn. All right, flip the page. Degree 3. What do you think? So degree 3, the arrows have to go opposite direction because 3 is odd. How many turns do you think it could have? 2. Okay, so we'll start with 2 here. So if I'll start on the bottom. So we'll turn, we'll go up 1 time, we'll turn. I have to turn again because my arrows have to go opposite. So it looks like I could turn twice and still have arrows going in opposite directions. There is another one. It's kind of hard because you don't know much about cubic functions, but cubic functions can actually turn 0 times. Now, what this looks like then is you would come up, you just kind of tilt to the side and go back up. So it's like you're increasing, you don't actually turn direction, you just kind of tilt and then keep going. That's not like the best graph I've ever drawn. Let me try that again. It's not the best cubic function I can do. Oh, well that looks better, but the highlighter's not great. There we go. That's a better cubic function. Right? So it comes up, it tilts, and it goes back up. The arrows are still going in opposite directions. And finally, degree 4, what do you think? Ideas?
0, 1.
Well, if I turn 1 time, I could turn 1 time, right? Remember on Friday we did a cubic, or quartic, I'm sorry, that had a really wide bottom, and I had 1 turn like that. The arrows still have to go in opposite directions. So I can turn once, the arrows both still go up. If I turn 0 times, that would be a line, right? So my arrows would be going in opposite directions. That doesn't work because it's degree 4, which is even. They have to go in the same direction. Sorry, I got you now. I'm on the same page again. I meant 1. Sorry. Yeah, better? Alright. I'm back on track. What else? 3. So 3, I'll start from the bottom this time. So if I go up, I could turn 1 time, 2 times, and then a 3rd time. Remember these are lines that kind of look like M's and W's? Now, this is the key information here that has to do with degrees. So on the right underneath here, it says it appears that the maximum number of turning points, the maximum number of times you can change direction, is equal to the degree minus 1. Alright, so if the degree is 4, the maximum number of times you can turn is 3, although you could turn fewer than that. Alright, make sense? Last little bit here. Let's talk about roots. X-intercepts. We'll mostly deal with X-intercepts here, but we are going to talk a little bit about imaginary at the end. So if I have degree 1, this is a line. Think about a line for me. How many X-intercepts can you have? 1, right? So if I have 1 X-intercept, I'll draw a graph like this. I cross the axis 1 time. Now what's another option? 0. Now we'll talk about this in a second, but I could have 0 X-intercepts. What kind of line would that be? A straight line. Now, that is a linear function. Now here's where it gets a little funky. Technically, yes, that's a linear function. It has no X-intercepts. But if I talked about the equation of that line, it'd be like y equals, I don't know, 3. That's technically the equation of a constant right there. So it gets a little funky, but we'll go with if there's 1 or 0 X-intercepts. All right, so technically it's constant, but we'll call it a line for now. It won't hurt anything. Degree 2, how many X-intercepts could you have? Think about parabolas. You could have 0 X-intercepts for a parabola, right? And that just means that you have a parabola that never crosses the x-axis. What other option of X-intercepts could you have? 1, okay, and that would come up, I'll do an upside down parabola, come up and touch the axis and bounce off, and we're going to investigate that, I think tomorrow actually. Why do you bounce off the axis? Okay, so that has 1 X-intercept, or you could have 2 X-intercepts. So you come down through the axis and back through, right? Yeah. Degree 3, cubit. What do you think? Could you have 0 X-intercepts? Why not? Because the arrows have to go in opposite directions. If it's odd degree, you have to have an arrow going down and up. So it has to cross the axis. So at a minimum, you can have 1 X-intercept. So for example, you could come up, squiggle up above the axis, but you only have 1 X-intercept. How many other X-intercepts would you have? You could have 3. Okay. So you could have 3 X-intercepts where you come up, back down through, and up again, bless you. So you have 3. What else? Could you have 2? You could have 2. We'll go the other way this time. I could come down. How about if I touch the axis here, come up, and then back down? That would give me 2 unique X-intercepts. Alright, last one. We're almost done. Degree 4. How many X-intercepts could degree 4 have? Can you have 5 X-intercepts for 4? I don't think that one will work. 4. Okay, we can have 4. So think about your M or your W graph, right? You could come down, and back through, and back down, and up. If I made a big W here, and that is 4 X-intercepts. Wow. You could make, wow, you could graph your name.
Wow, that's 2 W's.
You could graph a circle in the middle, and there you go. What do you research? Alright, how many other X-intercepts did you have? 3. Okay. So how would 3 look if I did 3? I could come down and through, but what has to be true about this other root? It just touches and comes back up. So that would be 3. What else? We're going to work backwards here. 2. So there's a couple ways you could do 2. You could come down and you could just touch and then touch again. That would be one way to do it. You could also, I'll come up above here. You could also make it go through and squiggle underneath. That would also be 2. There's lots of ways, and we're going to actually look more at this later in the week. Okay, 2 X-intercepts. What's another option?
1.
1. How would 1 look?
Only 1 would.
Yeah, just 1 touches, and then the other one just kind of squiggles up above the axis. And could you have 0? Yeah, you could have 0. The whole thing is above or below the axis. So here's the thing. We only looked at X-intercepts here. So it appears that the maximum number of unique X-intercepts is equal to its degree. All right, so the degree tells me how many unique X-intercepts I could have. However, in the box here, the number of roots, so roots are real and imaginary, is totally equal to the degree. So let me show you a problem on the next page. So this is your practice, but this is how your quiz will be set up on Wednesday. And we'll do a practice tomorrow as well. But this will be no calculator. You can check it on your calculator for today, but I want you to try your best to do no calculator here. So for example, let's talk about number 1, and then I'll let you up. I have -1 plus 3x squared. First of all, put that that polynomial in standard form. So I would put the 3x squared first, minus 1. That's standard form of the polynomial. What is the degree of that polynomial? 2. So I call it a quadratic. Okay, that's definitely, you don't need your calculator for that. Now the next part, the number of roots. So real, imaginary, any kind of root is always equal to the degree. So the number of roots will be 2. What are the maximum number of times this graph could turn? 1. It's 1 less than the degree. Okay, so roots is equal to the degree. The turning point is 1 less than the degree. Everything comes back to the degree. Now here's the part that's tricky without a calculator, that you need to think a little bit. If you need to, sketch a picture for yourself. I'm looking at end behavior. Now, if I have degree 2, 2 is even or odd? Even. So your arrows either both point up or they both point down. So you look at your leading coefficient. 3. 3 is positive or negative? Positive. So if it's a positive quadratic, that means do they both point up or both point down? Up. So you know, you don't have to make a picture if you don't need, but it'll look something like that. So that means both of these blanks, the arrows are going towards infinity. Okay? It's a little tricky, but slow down and think about it. I'll help you, and we'll do more practice the next couple of days. Okay? So try the rest of the back here. We're done. And we'll do warm up.